we have been discussing about the ionosphere, different properties of it, and about the production of ions in the ionosphere. And we also discussed the Chapman theory, which basically gives you we also discussed the Chapman theory, which basically explains the obtained curve of production in the ionosphere. So this is basically Q, and this is basically height. This is the curve that generally depicts the how the production of ions or electrons are changing with respect to height in the ionosphere. So Chapman theory basically derives the mathematical expression for this for the obtained curve. So we derive the equation. The production at any given Zola zenith angle and height h is given by eta into I infinity a rho 0 exponential minus h by h minus a rho 0 h c chi into e raised to minus h by h. This is the equation that we derived in the last class, where eta is the number density of electrons or ions. The number of electrons or ions per unit volume is eta, and chi is the Zola zenith angle. H is the height, capital H is the scale height of the atmosphere. A is the area of cross section of the vertical column. So this is the equation that we derived in the last class, which basically gives the production rate Q at any height h at any Zola zenith angle. Now let us find the equation corresponding to the peak production. Peak production in the sense at this particular point, what is the equation for the production? So that for deriving in case of peak production, so peak production is occurring and the rate of change of production with respect to height is basically 0. Q is Qm, production is peak production, the height at which is happening is the peak production height. So when this becomes 0, that's when peak production is happening. So if we substitute the equation that we got earlier, we will get d by dh of eta into I infinity a rho 0 exponential minus h by h minus a rho 0 h c chi e raised to minus h by h is equal to 0. Now if we find the derivative, we get, so this is a constant eta and I infinity a and rho 0 is constant, so this will go, when we find the derivative of this will be 0. So the equation will reduce to exponential of minus h by h minus a rho 0 h c chi into e raised to minus h into we have been deriving the equation for the peak production. So in the class we derived the equation for the production. This is given by Q of chi h is equal to eta I0 a rho 0 into exponential of minus h by h minus a rho 0 h into c chi e raised to minus h by h, where eta is the number of electrons or ions per unit volume, chi is the Zola's nth angle, x is the scale height, and a is the area of cross section of the vertical column that we are considering. Now, if we want to find the peak production height, or the value of peak production and the height at which the peak production is occurring, we are finding when this dq by dx is becoming 0 to find that peak. So for that we are doing the derivative with respect to h for the given equation. So d by dh of theta I infinity a rho 0 to exponential of minus h by h minus a rho 0 h c chi e raised to minus h by h. So in this case, eta infinity a rho 0, this term is a constant, so it will be 0 once we take the derivative. And if we take the derivative of the remaining terms, it will become exponential of minus h by h minus a rho 0 h c chi e raised to minus h by h into 1 by h, the derivative of this, plus a rho 0 h c chi into a raised to minus h by h into 1 by h. So thus h and h will cancel out. You will get exponential of minus h by h minus a rho 0 h c chi e raised to minus h by h into 1 by h plus a rho 0 c chi e raised to minus h by h is equal to 0. So this is the equation that you will get. So from this there is an exponential term and there is another term. So the exponential term cannot be 0. So this is basically equating to 0. Since the exponential term cannot be 0, the second term will be 0. Second term, exponential value will always be greater than or equal to 1. So the equation we can write 1 by minus 1 by h plus a rho 0 c chi a raised to minus h by h is equal to 0. That is the second term is equated to 0 since the exponential term cannot be 0. So we can write it like this and it will become a rho 0 c chi e raised to minus. We can write hn because we are considering when the peak production, the height at which the peak production is occurring. So h will be hn. So a rho 0 c chi e raised to minus hm by h is equal to 1 by h it will become, or we can write e raised to hm by h is equal to 1 by a rho 0 h c chi. So let this be equation number 1. Or if we want to, we are writing e raised to hm by h, in this denominator will become the numerator. We are getting rid of the negative sign. E raised to hm by h will become a rho 0 h c, or we can write hn, or the height at which peak production occurs is given by h log of a rho 0 h c. This is the height at which the peak production occurs. So the height height of peak production is given by h into log a rho 0 h c. So here there is no term with I infinity, so we can say the peak production height, is independent of the solar radiation, independent of the solar radiation at the top of the atmosphere. It is only dependent on chi. It is basically a function of the solar cycle. So suppose we are considering at noon time. Noon time in the sense sun is directly above the earth, so solar zenith angle will be 0. In that case, the equation reduces to Hn, let's write 0, which basically we not set 0 zenith angle, is equal to a rho 0 h into sec 0. Sec 0 is basically 1, and Hn 0 can be written as h log a 0 into h, or e raised to Hn 0 by h is equal to a 0. So this is another relation. So now we know what is the equation for the peak production height Hn. It is independent of I infinity, and it only depends on Hn is given by h log a rho 0 h into c. Now let's find what is the value of peak production. What is Qn? We will find Qn. So for Qn, Qn Hn is Q is a function of chi, and Hn can be written as eta I infinity a rho 0 exponential minus Hn by h minus a rho 0 h c chi e raised to minus Hn by h. Same equation, we are just substituting h with Hn. Now in this we can substitute this term. First we will separate it into these exponential, we will separate and write it into a raised to chi Hn can be written as eta I infinity a rho 0 into exponential of minus Hn by h into exponential of minus a rho 0 h c chi e raised to minus Hn by h. The exponential term I am just taking it out of the bracket. Now we know earlier we found the relation e raised to minus Hn by h. Here we found that e raised to minus Hn by h can be written as a1 by a rho 0 h c chi. Now we substitute that here for e raised to minus Hn by h here, and in the second term over here for this term we will get Q of chi Hn is equal to eta I infinity a rho 0. Instead of exponential of minus Hn by h we will write 1 by a rho 0 h c chi into exponential of minus a rho 0 h c chi. Here also we will substitute into 1 of chi hm becomes, here a rho 0 will be gone. Here the whole term will be gone. A rho 0 xc chi, a rho 0 xc chi. So it will become eta I infinity 1 by xc chi, or eta I infinity by xc chi into e raised to minus 1, or we can write Q, peak production Qm is given by eta I infinity by h e, this is e raised to minus 1 into cos chi. 1 by c chi is cos chi. So this is the equation for the peak production. Equation for peak production Qm is given by eta I infinity cos chi by h into e. So here again at noon time, how it will become at noon, when chi is equal to chi equal to 0, the equation will reduce to Qm at zeros and angle and high tension is given by eta I infinity by h e, or we can write eta I infinity is equal to Qm zeros and angle into h into. So this is another relation. So we will simplify the equation that we got for Q of chi h using by substituting some of these relationships. So we can write the equation for the production any height h and at any solar length angle chi has. So eta infinity is there in that term, right? So here we have eta infinity. We just saw eta infinity can be written as Qm into h. So we can substitute that. So the equation will become Q of chi h is equal to, we will substitute eta infinity as Qm 0 hm into he into a rho 0 exponential minus h by h minus a rho 0 h c chi into e raised to minus h by. Now again we know e raised to hm by h is equal to a rho 0 into h. Earlier we found this relation, e raised to hm by h is equal to a rho 0 into h. Now if we substitute this, it will become Q of chi h is equal to, so here a rho 0 h can be substituted by a raised to h. Q chi h is given by Qm of 0 hm into e raised to hm by h into e, this e is there, into exponential of minus h by h minus a rho 0 h c chi a raised to minus h by h. Lot of exponential terms are there, right? Now we will just combine all these exponential terms so that we can see, we can simplify the equation further. So after combining the exponential term, we can write Q of chi h is equal to Qm of 0 hm into exponential of 1 minus hm by h just combine the exponential terms. So this term, now we can define another variable for height. Define another variable for height. Z, which is given by h minus h by h. This term can be replaced by z. So the equation finally simplifies it into q of phi h is equal to qm of 0, h into exponential of 1 minus z. H minus h by h will become z. 1 minus z minus c chi. Here also we have h minus h1 by h, so it will become e raised to exponential of q by qm can be written as exponential of 1 minus z minus c chi into exponential of minus z. This is the final equation for the production for any Zollhagen triangle chi and any height h. Now we will see what are the major inferences that can be derived from these equations. The major inferences are the first one, peak production rate happens at a height when the product n sigma is equal to or n is equal to 1 sigma. N is the total number of atoms or molecules, and sigma we know is the absorption cross section. So when n sigma is equal to 1 is the time when peak production happens. The second one, the rate of production is given by Q is equal to Qm into exponential of 1 minus Z minus exponential of minus Z into C chi. Minus Z into C chi. The third one, so basically this equation which has an exponential within an exponential will give you the shape of curve. This mathematical expression will give you the shape of curve. And the third one, the peak production rate is given by Qn is equal to eta I0 cos chi by He, or zeros and a triangle given by Qm0 is equal to eta I infinity by He. So the peak production is independent of the cross sectional area that is absorbing this radiation. This basically means it is independent of sigma. production is independent of the peak production is independent of the absorptional cross-sectional area. Now, if we are how the curve is changing, or the peak production and the height of peak production is changing with respect to the Zola's angle. Suppose this is Q, this is H minus H1 by H or Z. So this is the equation. This is the curve for when Zola's angle is chi is equal to 0. Now we increase the, we know that Hn is given by H into log A rho 0 H C chi. And also Q by Q, also Qm is equal to this is Hm, and Qm is equal to eta infinity by He into cos chi. So when chi is equal to 0, this is the value of Qm. This is the peak production height H. Now we increase the Zola's angle. Cos chi from 0. Suppose if we are increasing 0, we are increasing to 30 degrees. The value is around 0.86. So from 1 it is decreasing to 0.8. So the value corresponding to Qm will be less than, so when the value corresponding to chi is equal to 0 of Qm will be less than when chi is equal to 30. Because in this case cos chi is equal to 1. Then in this case cos chi is approximately becoming 0.8. Whereas in case of height or the peak production, the height at which the peak production is occurring, Hm. Yeah. And when we look at the height at which the peak production is occurring, that is Hm, is having C chi. So it is basically 1 by cos chi. So as the denominator is, initial case it will be 1, and in the second case when the denominator is becoming 0.8, the value is greater than 1, or it is 1.25. So Hm will be increasing, whereas Qm will be decreasing. So as chi is increasing, Qm is decreasing, and Hm is increasing. Suppose this is the curve for chi is equal to 45. Hm is higher, whereas Qm, the value has decreased. This is chi is equal to 30. Now we further increase it maybe to 45. This is the height, which is higher than these two, and this is the, so as the Zola's angle is increasing, the Qm keeps on decreasing, whereas the height at which the peak production occurs is increasing. That is the, so we can say the maximum peak production, maximum Q we are getting, maximum production is happening when chi is equal to 0. Production, also the height, and the lowest peak production height. Production peak at lowest altitude for chi is equal to 0. Peak production high is the lowest for chi is equal to 0. And as chi increases, the Rologen angle is increasing, the production is decreasing. Also, as the chi is increasing, the height of peak production is increasing. And since Hm is given by H log Hm is given by H log A rho 0 H C chi. The height of peak production is independent of I. Independent of I. So these are the main inferences from the Chapman theory. Now we will go to another topic, which is basically hydrogen in the atmosphere. So we know that hydrogen is very light. It is the lightest atom. So the impact of gravitational pull on this particular atom will be very small because of the lower mass of the particle. So basically, the hydrogen atoms or molecules occupy generally at a very high altitude in the atmosphere because of this lighter weight. And since it is almost since it is at very height, it is located at very higher altitude. It interacts with very high energy solar radiation. So because of the uh, lightest atom, and it occupies at a very high altitude, very high altitude in the atmosphere. It occurs at very high altitude in the atmosphere. And since it is at the top of the atmosphere, it interacts with high energy solar radiation. It interacts with high energy solar radiation. So as the hydrogen atom encounters the incoming solar radiation at very short wavelength, so suppose less than 90 nanometer, it ionizes into hydrogen ions and electrons. This process is known as photosynthesis. We are already familiar with this. We have learned it, and we learned the ion formation here. So hydrogen atoms interact with high energy solar radiation of wavelength less than 90 nanometer and produces hydrogen ions plus electrons. And these hydrogen ions interacts with neutral oxygen atoms and undergo a process known as charge exchange and again becomes neutral atoms. Charge exchange process. So the formed hydrogen ions interact with neutral oxygen atoms and undergo a process through the process of charge exchange again becomes neutral atoms. So we want to find the concentration of hydrogen atoms at any point. The concentration of hydrogen atoms is given by concentration of hydrogen atoms is directly proportional to the concentration of H plus ions and that of oxygen. Therefore, we want to find the concentration of hydrogen ions. It is given as concentration of hydrogen atoms by the concentration of oxygen atoms. So we know the number density of electrons or ions are given by n is equal to n0 exponential of minus h by h. This comes from p is equal to p 0 e raised to minus h by h. It applies to density, number density. So scale height h, which is basically RT by mg, is a function of the particle itself. In case of oxygen, the scale height can be called the scale height of oxygen, and in case of hydrogen, we can call it the scale height of hydrogen. So this equation we can substitute here. So the concentration of H plus ions, the concentration of hydrogen atoms is proportional to e raised to minus h by the scale. At any height, h is given by e raised to minus h by the scale height of hydrogen atoms. So this given by. So this is basically concentration of hydrogen atoms, neutral atoms by concentration of oxygen. So it will become exponential of minus h by proportion minus h by scale height of hydrogen divided by exponential of minus h by scale height of oxygen. So when it comes to numerator, it will become plus h by scale height of oxygen. So the concentration of H plus is proportional to exponential of minus h by scale height of hydrogen plus h by scale height of oxygen. Now the scale height of oxygen and scale height of hydrogen, the ratio between the scale height of oxygen and scale height of hydrogen will be the ratio between their masses itself. Since H is given by RT by mg, the ratio between scale height of hydrogen and scale height of oxygen 1 is basically 1 is to 16. Or we can write the scale height of hydrogen is equal to 16 into the scale height of oxygen. If we substitute this in the equation, the concentration of hydrogen ions become exponential of minus h by 16 into scale height of oxygen plus h by scale height of oxygen. So it will become concentration of hydrogen ions is proportional to exponential of 15 h by 16 into scale height of oxygen. So this is the concentration of hydrogen ions in the atmosphere. So this equation shows, will give you a pattern like this, since it is positive expansion, which is different from the general distribution of other elements. The general distribution that we get given by, this is the general pattern that the vertical profile of most of the atoms or ions, whereas in case of the hydrogen ions, it is the opposite, that it is increasing with respect to height in the atmosphere. No other particle has a profile like that. Is the peculiarity of hydrogen ions in the atmosphere. Now we will move on to another topic, which is Debye shield. Debye shield. Debye line. Generally, if we have a positive charge somewhere in space, suppose we have a positive charge somewhere in space, the electric field that is exerted by the positive charge is given by or is proportional to the distance from the charge. At this point, we are finding the electric field. It will be inversely proportional to the square of the distance between the charge and that particular point. So basically, it decreases by 1 by r square. So it will decay very fast. So at whatever distance that we take, we will have an electric field associated with this particular charge. Now suppose consider we are placing this positive charge within a plasma. So plasma, we know, is basically ionosphere is plasma. So plasma is a gas which has high density of ions or electrically conducting, high density of ions or electrons. So plasma is basically a gas which has high density of ions or electrons. So suppose now you are placing this positive charge within a plasma. What happens is that after a particular the plasma will behave as if it will confine the influence of this particular charge. So plasma means it has both positive and negative charges. As we have discussed earlier, it is considered to be quasi-neutral, which means the net charge will be 0. So this is a plasma. Now we are placing, generally if we have a positive charge, no matter at whatever distance we take, it will have an electric field associated with this, which will be decaying as the square of the distance between that particular point and the charge. Now we are placing this particular charge within plasma, which is an electrically conducting material, which has both negative charges. So what will happen when we place this positive charge within a plasma is that it will confine the influence of this charge up to a certain point, after which the rest of the plasma, the remaining plasma, will not be coming under the influence of this charge or will not realize that there is a charge that is present at some point in the plasma. So generally in space at whatever point we take, we will feel the presence of this positive charge. But when we keep this charge within a plasma, after a particular distance from the charge, the plasma will confine the effect of this positive charge like that up to a certain point. The rest of the plasma will not be coming under the influence of this charge or will not realize that a positive charge is present at some point in the plasma. So if we place a charge in the plasma, it will attract opposite charges and repels like charges from it. So once we place the charge within it, the plasma has both positive and negative charges. The charge will start attracting negative charges towards it, whereas it will start repelling the positive charges. it will start attracting negative charges towards it and it starts repelling the positive charges. So the electrons will form a shield kind of thing over the positive charge, so that after a particular point the effect of this positive charge won't be felt. So this is basically known as the Debye shielding. So the opposite charges will form, if it is a negative charge, a cloud of positive charges will be formed. So when you keep a positive charge inside a large number of freely moving charges or a plasma, the charges of opposite polarity is immediately attracted to this test charge and they form a cloud in the vicinity of the test charge. Since the charge is positive, a cloud of electrons are formed. If we are keeping a negative charge, then a cloud of ions will be formed. So this will trend to this cloud of electrons, or this cloud of electrons tends to neutralize the test charge. So it won't go the random motion. The particle is in constant motion. So it won't allow the particles to go to the test charge and stick to it. That it won't neutralize. But because of the presence of this cloud of electrons, the effect of this positive charge will not be felt outside a particular distance. So generally, because of the Coulomb attraction, if a positive charge is kept in a pole of both negative and positive charges, one electron should come, one negative charge should come, it should combine with the positive charge and then neutralize. But due to the random motion of the positive and negative ions within the plasma, this recombination is not happening. But a cloud of electrons is formed surrounding the plasma, surrounding this positive charge. This process is basically known as Debye shielding, and the length up to which the effect of this positive charge is felt is known as the Debye length. If the distance is exceeding the Debye length, the effect of this positive charge won't be felt. So what will happen? We have plasma which has both positive and negative charges. We are placing a positive charge, test charge within it, so a cloud of electrons will be formed around the plasma so as to neutralize the effect of this positive charge. The positive charge will be surrounded by negative charges. The negative charges, or whatever it may be. In this case, I am considering a positive test charge, that's why it is negative. If it is a negative test charge, then positive ions will come and form a shield. So the negative charges form a cloud or shield around the positive test charge. So the electrons outside a particular length will not feel the attractive force from the test charge cube. The radius of the sphere, the radius an electron outside the sphere will not feel the attractive will not feel the attractive force from the charge, from the test charge Q. Outside the sphere, no electrons will feel the attractive force from the charge Q. The radius of the sphere is called d by lambda. This is lambda. And the process of shielding, the process of shielding is Debye shielding. Now let's find the expression for the Debye lambda d, which is after this distance, the effect of the positive charge won't be felt. The distance up to which the positive charge will have an expression for Debye. So we have plasma adding a positive charge to it. Cloud of negative charges will be formed around the plasma. So we are adding charge Q to the plasma. The potential felt by the charge P of R is given by 1 by 4 pi epsilon 0 Q by R. Potential associated with the charge Q is given by 1 by 4 pi epsilon 0 Q by R. At T is equal to 0, when we just added the T is equal to 0, the area of R is given by Q by 4 pi epsilon 0 into R. This is the potential associated with the charge initially. At T is equal to T, after some time, the negative charges will get attracted to the negative charges will get attracted to the positive test charge and form a cloud around it. Since the mass of electrons is very much less than the mass of ions, the velocity of electrons is very much higher than the velocity of ions. So since velocity of ions is considered to be at rest. within the sphere, the NE is less than is very much greater than I. So it will lead to a charge density. Within the sphere, NE is very much within the sphere in the sense we have the positive charge and we have the electrons surrounding it. So within the sphere, the number of electrons is very much greater than the number of ion or number of positive charge. So there will be some charge density associated with this, which can be given by rho. Rho is the charge density. So the electric field E is given by del dot E is given by rho by epsilon, where rho is the charge density. So del dot E can be written as rho is the charge density, which is Q into the number density. So number density is basically Ne minus Ni. N is the total number of electrons per unit volume and Ni is the total number of ions per unit volume. Q is the charge corresponding to Q is the charge value. So del dot phi can be written as Q into, since Ne is negative, we can write minus Q into Ne minus Ni by epsilon 0. And Q was basically the charge of electron. So we can write del square del E is equal to minus E is already minus E into Ne minus Ni by epsilon 0, or we can write del square phi is equal to E into Ne minus Ni by epsilon 0. Now we will find what is Ne and Ni. So assuming the thermodynamic equation and Maxwell-Boltzmann theory, we can write assuming thermodynamic equation and Maxwell-Boltzmann theory, we can write N is equal to, how it changes, N0 into minus E by AB into T, or F of N is equal to A into exponential of minus half mu square plus E phi divided by AB into, this is the kinetic energy associated and this is the potential energy. The detailed derivation is there in your detailed class. I'm not going into detail. So the number of ions Ni will be equal to N0 itself. Since we are considering it as background, since here the velocity is small, we are considering that the ions are at rest. Ni will be N0 plus Ne will become N0 into exponential of minus E by AB into T. So del square phi can be written as minus E by epsilon 0 E by epsilon 0 N0, this is E by epsilon 0 Ne minus Ni it is E by epsilon 0 Ne minus Ni. Now we substitute Ne is equal to E by epsilon 0 Ni minus Ni. Now we substitute Ni is equal to N0, Ni can be written as n0 into exponential of minus E by kb. It can be written as minus E by epsilon 0. Here also one negative n0 minus n0 into exponential of E by kb. So E is equal to minus E phi. Substitute that, it will become minus E by epsilon 0, n0 minus n0 exponential of E phi by kb into t. And now assuming E phi, the value of E phi is very much less than kbt, exponential of E phi kbt can be written as 1 plus E phi by kb. So it will reduce to del square phi is equal to E square n0 by kbt into epsilon 0 into phi. Or we can write del square phi is equal to phi by lambda d, where lambda phi by lambda d square, where lambda d square is given by kbt epsilon 0 by n0 into d square, or lambda d is equal to root of kbt epsilon 0 by n0 into d square. This is the equation for the Debye length. The length up to which the effect of the positive effect of the charge will be felt, after which the length r is greater than lambda d, then the effect of the external charge won't be felt within the flux. So this is the length up to which the effect of the test charge would be felt outside the Debye sphere or outside this line. The effect of test charge won't be felt due to Debye shielding. The effect of test charge won't be felt about outside the Debye line. From here we can see, from the equation we can see lambda d is proportional to root of temperature and is inversely proportional to the root of number density of electrons or ions in the plasma. From the equation we can write lambda d is proportional to root t and lambda d is proportional to 1 by n0. Suppose there is high temperature. High temperature means thermal energy is high. So electrons are, so because of the high kinetic energy of the electrons or ions present in the plasma, it won't be able to form a proper sphere around the positive charge. It will keep on moving. So because of that, the Debye length will be very large. Whereas when the second one is it is inversely proportional to the number density. Because if the number density is very high, then the just close to the positive charge itself, if n0 is less, it will be so much scattered. Charges will be so much scattered. So the Debye length will be high, like up to which the effect will be felt will be high. Whereas if the density is very high, it will be closer itself, it will form that. So lot of charges are there. So closer itself, it will form the Debye, very close to the charge itself. So the Debye length will be less. So that is the dependence of Debye length on temperature and the number density of electrons are. So now we will look at another term which is known as the Debye potential. Debye potential given as phi of r. What is Debye potential? As del square phi is equal to phi by lambda d square, where lambda d is the Debye length. And lambda d is given by root of kBT epsilon 0 by n0 d square in meters. So in spatial coordinates, just r, theta and phi, the del square term, expansion of the del square term is given by 1 by r square dou by dou r of r square into dou phi by dou r plus 1 by r square sin theta into dou by dou theta of sin theta into dou theta by dou phi by dou theta plus 1 by r square sin square theta into dou square phi by dou phi square. This is the expansion of del square in spatial coordinates r phi and r theta and phi. So phi r, or the potential phi r, is symmetric about theta and phi. So because it basically doesn't vary along theta and phi direction. Because of this, dou phi by dou theta is equal to 0. Also, dou phi by dou phi is also equal to 0. The del square will simplify into 1 by r square dou by dou r into r square into dou phi by dou r. So we can write 1 by r square dou by dou r of r square into dou phi by dou r is equal to phi by lambda d square. Now we solve this. We get an equation like phi of r is equal to 1 by 4 pi epsilon 0 q by r into a raised to minus r by from the Coulombic potential, there is an additional term, which is e raised to minus r by lambda d. This is the potential inside the plasma. So this is the exponential decay, additional exponential decay term, and we are considering the charge, test charge within the plasma. This is the Coulombic term, general. So generally, when we have a positive test charge, the potential decreases as 1 by r square. Now, since it is within the plasma, what happens is that initially it will decrease like this. Then after the Debye length, lambda d, it will start decaying exponentially. This is 1 by 4 pi epsilon 0. This is 1 by r term. Decay as 1 by r. Here in this case, it will be decaying by e raised to minus r by lambda. Now let's find out what is the potential when r is equal to lambda d. The distance is equal to lambda d at r is equal to lambda d. Pi of r reduces to q by 4 pi epsilon 0 first term, q by 4 pi epsilon 0 into lambda d into this one will be minus 1 e raised to minus 1. So it will be 4 pi epsilon 0 into lambda d into d. And then r is equal to 2 lambda d. Potential will reduce to pi of r is equal to q by 4 pi epsilon 0 2 lambda d into it is keeping on decreasing as the distance is increasing. So that is about the Debye length and Debye potential. Now we will learn another term which is known as the plasma frequency. Let's see what is plasma frequency. So the frequency associated with electrons or ions in the plasma. That is the plasma frequency. Consider that the electrons are displaced from its initial position to some distance. Okay, so suppose this was the initial location A. It is displaced from A to B. Now since the electrons are being displaced from this point to this point, here there is a deficiency of electrons, which will be shown as the positive charge. Like this. So now, since there is a charge separation, an electric field will be formed. This positive to negative, and it will try to bring the electrons back to the initial position. Like this. The electric field will try to take the electrons back to its initial position. But because of this mass, some of the electrons may overshoot and will be displaced somewhere. Instead of A, it will go some more distance. So because of this separation, another field E2 will be formed. And this electric field will try to displace the electrons back to the initial position again. So the electrons will basically be oscillating with respect to the initial position A. So the frequency of oscillation, so basically this frequency of oscillation is known as the plasma frequency. Let's see how to find the equation for the plasma frequency. So this looks like a parallel capacitor. Positive. This is the positively charged plate. This is the negatively charged plate. The surface charge density. The surface charge density in the plate is given by sigma is equal to Q by A, where Q is the total charge, which is given by N0 number density into electron into delta X, which is basically the distance between the initial position and the final position. And the electric field E, sigma by epsilon 0, which is equal to minus E N0 delta X by epsilon 0. So there will be a force. This is the electric field. So the force exerted is basically given by mass into acceleration, which is equal to mass into d square. Delta x is the distance that is being moved. D square delta x by dt square. So electric field is basically providing the force to take the electrons back to its initial position. So we can write m into d square delta x by dt square is equal to the electric field, which is given by minus E N0 delta x by epsilon 0. It will become so d square delta x by dt square will become d square delta x by dt square will become minus E N0 by m epsilon 0 into delta x. This quantity d square delta x by dt square is equal to minus omega p into delta x. This is known as the angular frequency of the oscillation. Angular frequency angular frequency. So we want to find the frequency, angular frequency given by frequency by 2 pi, or angular frequency by 2 pi is the actual frequency. Plasma frequency f is given by omega p by 2 pi, which will be E n0 by m epsilon 0 into 2 pi. So all these are constants. Like the value of electric charge we know, value of the mass of electron we know, value of electron we know, 2 pi is also known. So once we substitute and find the values, it will be 9. So 9 and the square root of n0. Plasma frequency is basically given by 9 into square root of n0. This is the equation for the plasma frequency. So today we discussed about the inferences that we have made from the Chapman theory, the equation for the peak production height, equation for peak production, and we learned what is Debye shielding, what is Debye length, Debye potential, and finally what is plasma frequency as well. we will try to solve one of the equations based on the things we just learned. The question 1. What is the scale height of the atmosphere? What is the scale height of the atmosphere if it consists of oxygen atoms and temperature is 27 degrees Celsius. So when we discussed about the concentration of ions in the concentration of hydrogen ions in the atmosphere, I told that the scale height is actually a function of a particular gas, or it depends on the gas that we are considering. We know that the equation for scale height H is equal to RT by mg. So here the R, we need to find correspond. This is not RD. This is the universal gas constant R. So the scale height R will become 8.314 joule per Kelvin per mole divided by the mass of oxygen, which is 16 into 10 raised to minus 3 kilogram, into temperature is given 27 plus 273 will give you 300 into 9.8. So the answer will be 8.314 into 300 divided by 16 into 10 raised to minus 3 into 9.8. The answer will be 15.9 kilometer, or approximately 16 kilometers. So this will be the scale height of the atmosphere at a temperature of 27 degrees Celsius, which is consisting only of oxygen. Just give me a minute. Now we will try to solve another question. If the electron density of an ionospheric layer is 2 into 10 raised to 11 per meter cube, calculate the plasma frequency at 850 degrees Celsius. So we know the equation for the plasma frequency is given by 9 into root of n0. It is independent of the temperature. So we don't need the value 850 degrees Celsius. Frequency is given by 9 9 into root of 2 into 10 raised to 11. How much it will be? It will be 4 into 10 raised to 6 hertz. It will give you a value of 4024 hertz, or you can write 4 megahertz. This is the value. For the previous question, what will be the number of particles in device sphere? There is another parameter which is known as the plasma parameter, given by this. This is known as the plasma parameter. It basically gives you the number of particles in the device sphere. So since it is sphere, it will be 4 by 3 pi r cube. So the radius of the sphere is basically given by the Debye line. So 4 by 3 pi lambda d cube into number of particles we need, volume into number, so into n0. So in this case, they have given the value of n0, which is 2 into 10 raised to 11. N0 is given as 2 into 10 raised to 11. Now if you want to calculate the plasma parameter, which is given by 4 by 3 pi lambda d cube into n0, we need to find lambda d first. So lambda d is given by epsilon kBt by n0 into e square. T is given as 850 degrees Celsius, which is 1123 Kelvin. Boltzmann constant is having a value of 1.38 into 10 raised to minus 23 joule per Kelvin. Epsilon 0 is 8.6 into 10 raised to minus 12 Newton meter square coulomb square. The charge of the electron is 1.6 into 10 raised to minus 19 coulomb. So lambda d will be root of 8.6 into 10 raised to minus 12 into 1.38 into 10 raised to minus 23 into 1123 Kelvin divided by 2.11, which is n0 into 10 raised to 11 into e square, which is 1.6 into 10 raised to minus 19 the whole square. This will be answer will be approximately 5.17 into 10 raised to minus 3 meter. Now we substitute this to find the plasma frequency. It will become lambda is equal to 4 by 3 pi into 5.17 into 10 raised to minus 3 the whole cube into 2 into 10 raised to 9. It will give you a value of around 115768. This will be the number of particles in the device. Now, next question. Given the electron density of plasma to be 10 raised to 20 per meter cube, what is the Debye length if the temperature is 1300 Kelvin? Electron density is given as 10 raised to 20. Debye length we need to calculate. Temperature is given as 1300. We know Debye length is given by root of epsilon 0 kBT by n square into t square. If we substitute, it will become 8.85 into 10 raised to minus 12 into kb plus 1.38 into 10 raised to minus 23 into 1300 divided by n0 is 10 raised to 20 into 1.6 into 10 raised to minus 9. This is the charge of electron got. The answer will be 2.49 into 10 raised to minus 7. Now we will do one more problem. Then I'm done today's session. At 1200 Kelvin, the plasma frequency is 2 megahertz. Calculate the Debye length. This is also to calculate the Debye length. Temperature N0 we don't know. We only know the temperature. Temperature is equal to 1200 Kelvin. We also need N0 to calculate Debye length. Instead of N0, they have given frequency of plasma, which is 9 into root of N0, which is given as 2 into 10 raised to 6. So N0 will be 2 into 10 raised to 6 by 9 the whole square, which will be 4.93 into 10 raised to 10 per meter cube. Now we calculate lambda d for the Debye length. Lambda d will be root of epsilon 0 kBT by n0 is, which is root of 8.85 into 10 raised to minus 12 1.88 into 10 raised to minus 23 into 1200 divided by 4.93 into 10 raised to 10 into 1.66